activity in a little bit. Okay, don't worry about it right now. What I do need you to worry about though is make sure you have a calculator. There's some around on the desks. If there's not, or if you don't have one, see if there's one near you. Did we enjoy our little surprise on Friday? I did too. Cause you what? Oh, you guys missed your field trip. Yeah, bummer. Are they making it up? No. Oh. It's only that day. Yeah. I'm sad. Yeah. I'm sad because that would have been a good experience for you guys. But you didn't miss class, right? I mean, honestly though, there was probably no one going to be here anyway, so we probably wouldn't have done anything. But oh well.
We just not do anything today.
No, we are. We are. On page 298, we left off on Thursday talking about properties of exponents, how we can use those to help us solve equations. But we eventually got to a point where we could not use properties to help us solve, and that's why we had to use a calculator, because this can help us in difficult situations. So we're going to review how we can use the calculator to help us find a solution, and then we'll get to our little envelope activity that I passed out at the beginning. Okay? So let's take a look at number 1. If we thought about solving this one by hand, we unfortunately cannot get the bases to be the same, because there's no way you can make or turn a 2 into a 3 or a 3 into a 2 by using like bases. So we're going to graph it on our calculator and see if we can find that intersection point. So do me a favor, turn on your calculator, clear out anything that's in there. I mean, maybe this problem's in there from last period, but make sure it's the right one. All right, in y1, we're going to type in the left-hand side, 2 to the power of x plus 1. And in y2, we'll type in the right-hand side, 2 to the power negative x plus 2. Before you hit graph, let's make sure our window is something semi-appropriate. Okay, we don't really know what a good window should be, but we could probably guess that anything into like the 50s or the hundreds is probably not going to be a good window. So right now I have -6 to +6 in each direction. Who knows if we'll have to change it or not, but we'll start somewhere. Yeah. All right, let's hit graph. I'm trying to figure out where are these equations the same. So graphically, I'm trying to figure out where do they cross or where do they meet each other. So I definitely have an intersection point right there. The question is, do we remember from Thursday, I know it was a long weekend, what buttons we press to get the calculator to tell us that spot? Yeah. There we go. Okay, second trace, our go-to menu for anything graph. Choose option 5. Okay, so far so good. This is telling the calculator we want to find an intersection, but how do you tell the calculator how to find it? There's a little bit more we have to do. Yeah? Okay, move the cursor to where they cross, where you think it is, and hit enter 3 times. 1, 2, 3. Alright, so we're going to write down the x-coordinate, that's our solution, the spot where these two equations meet. So we'll write down the x value. Do you guys think you can do the other 2 examples? Graph them, try to find the intersection point. See how you do. Try 2 and 3.
Assuming it's going to be separated based on if it goes down. Oh, guess what? We're together now because
the worst name you can call your mother is blood.
C is what?
Blood rain.
Okay. It's not necessarily any equal amount of each group for the space
That's the
below.
worst word call your mother.
If it goes down or up. One goes down. You got ups over there too. Well, that was just I'm doing. It's good. Yeah, this is. I'm at the house with
I love how you don't have to even
not necessarily equal amount.
you press enter 3 times.
This is a. Technically goes up. Does it count? This is the roll. I'm still considering just this part. Excuse me.
Wait, ours are 1 number off.
This is grow.
That's it. Such other name. I'm better than you.
Yeah, there's 5 more. That's good.
Was it literally
One equals up.
It was 1 number.
Wait, one. It is equal. But I feel like it's not supposed to be equal. So I got messed up. It's only supposed to be 2 groups. Yeah, I don't know. Give us some more information on what we're supposed to divide this. You have to figure that out. Well, there's like 5 different things.
Tuesday and Wednesday.
There's like 5 different properties and combined.
Sucks. Why? You work Monday and Tuesday. I work.
Any luck with number 2? Yeah?
I don't know if I work this weekend.
3.415. Sound good? All right, what about number 3? Did we get there yet?
Almost.
Almost? Yeah. 1.02. Okay, I got 8. Sound good? Are those all of our intersection points?
No.
Number 3 should have a second one.
Do an arc about a bunch of ants.
Yeah? 4.549. Okay. How do we do? Were we able to catch that number 3 had 2 of them? Do we have to talk about any of those? Speak now, forever hold your peace. You're holding your peace. All right. So now that we are starting to get a little bit comfortable with exponential functions, we're really going to start to dive into how the equation and the graph are related to each other. Just like we did with rationals, our ultimate goal is for me to give you a graph and you write the equation, or me give you an equation and you write the graph. Okay, we're going to try to do that same ultimate analysis with these exponential functions. So to kind of kick things off, just to get us into the mindset of what characteristics we should be looking for, I want you to do a little exploration with the envelope that I gave your little group. You will have to spread out these 12 graphs on your desks, so maybe try to make a little bit of room for you to see all of those. But you should also have this page 301 available for you to jot some things down. Okay, so open up your envelope. There should be 12 little cards. Make sure you have 12 of them. If you're missing one, let me know.
Give Robbie that one.
Robbie gets this one.
You get this one.
I get this one.
Probably.
Oh, do I get 7?
You're all gonna have to see them at once. So maybe put them on
Yeah, we're on
Lincoln's
the
desk.
So,
We good?
he just gets stuff, that's it.
We got all 12?
I'll see them, Leonard.
They should be numbered.
Them all on your desk. You're so powerful.
Leonard, I know. Give me the power. I need the power. Gotta do the big space. I need kind of 9.
15.
All right. What we're going to do is start to look for little characteristics either within the equation or within the graph to start to make the connection between the two. Okay, we're definitely not going to make any connections today. It's going to happen throughout the rest of this unit. But today is just for us to get used to what are those little things that we can look for in an equation or a graph to help us make that connection. So what I want us to do first, looking at all 12 of your cards, I want you to only look at the equation. Do not worry about the graph just yet. Okay, only look at the equation. I want you, are we listening? I want you to divide your group of 12 into 2 groups. They do not have to be equal groups. Okay, you don't need 6 and 6. Maybe you have 2 and 10. Okay, I don't know. But I want you to divide them into 2 groups based off the equation only. Okay, don't worry about the graph. So everything in group 1 should have something in common, and everything in group 2 should have something in common. Okay, based off the equations only. I'm not telling you what to look for because I want you to see what you first notice. Okay, and then we'll talk about all of our little differences. Okay, so divide them into 2 groups just based off the equations. I'll give you a few minutes.
We're not supposed to look at the graphs.
Oh, sorry about that.
You want to do one that's 1 to 11? No, 2 and a half, 2 tens, 3.
Robbie, you gonna help us? We already stop texting your girlfriend. Stop texting that. Like she doesn't care about you.
That's about the
Who covered up the numbers? Who pushed it so that now I can't see my name? What did you do? I don't do so nicely. Look at the equations and something that's different.
second is positive. But this is like the exact same Is there one with just a negative?
I don't know.
There's like 1 or 2, 3. There's 3 of them that and 9 of them. Yeah, 2 groups. Wait, did she say if they're going to be
Sure, let's do it. Yeah.
That's definitely not it.
Okay, Baba knows what he's doing. Oh, wait, maybe if it's a negative. Well, that's a different
I am certified genius. No, there's like no negative.
Oh,
There's 3. There's still 3.
The fraction itself doesn't matter.
There's 3. Fraction is no, it's that's right.
So like I think whole, I think if it's a whole number and a positive.
I get the sense that these are commonplace.
I don't think.
Yeah.
See, look, it's a whole number and it's positive, and it's a whole number.
There's another one. Missed it.
Alright, so we contrast these. This is a lot more.
No,
This is a lot better.
Hey, go look at the graphs. What are you doing?
It's too early.
Go look at the graphs that are just the
Showing
equation.
us how
Just the equation.
Is there one that shows us how negative yesterday is? Use word
Put a
contractions.
piece of tape.
Put a piece of clear tape on top. Piece of clear tape.
Do we have our two groups? Yeah? All right, we're going to start to share. I'm going to go head around, and once I get to your group, I want you to share one of your groupings. Okay, because if you share one, we can kind of think about what was the other one. Can you give us one of your groups, Caitlin? Can you list the numbers?
1, 5, 7, and 11. Because they all only have one exponent.
What do you mean by one exponent?
Like it's just to x or negative x instead of having x plus 1 or x minus 1.
Okay, so they looked at the powers. So I'm going to bring two of them up here. So notice how in number 1, the exponent is just a single x, whereas in some of the other examples, it was like x plus 2, x minus 5, something like that. Okay, so based off the equations, they noticed that connection. So these ones had only x in the power location. Okay, only x in power, nothing else. Ladies, can you give me one of your groups, Olivia and Elsie?
7, 9, and 11.
What did all those have in common?
They all have negative exponents.
7, 9, and 11. Okay, so looking at the powers, notice how in some of the cases the x was negative, but in other ones the x was not. Okay, so x in power is negative. Okay, so I'm assuming all the other ones didn't have that. Okay, Erica's group, can you give us one?
We have 8, 10, and 12. And the leading coefficient.
Ooh, so different negative spot. Okay, so here's 8, and then we'll take a look at 5. Okay, so instead of looking at a negative in the power spot, maybe we can take a look at a negative out front, okay, in that leading coefficient location. So we'll say leading coefficient is negative, okay, for those examples. I like it. Gentlemen, did you think of one?
Yes.
Okay.
We got 4, 2, 5, 9, 3, 11, 8, and 10.
4, 2, 5, 11, 3, 8, 10.
I think you missed 9.
I missed 9 and 9. Okay.
Okay, and then that one's whether the leading coefficient is a fraction or if it's a whole number. Those are all fractions.
The leading
Or
coefficient.
just like the main number thing. I don't know. Whatever you call it.
What's the main number thing called? A base. Okay. So yes. So the number sometimes it's in parentheses, sometimes it's not. Okay, but whatever is being raised to a power, that's called your base. So, for instance, 2 had a base of a half, 7 had a base of 2. So you're saying all these had, what was your connection? Fractional?
Fractional, they're all fractions.
Okay. Fraction bases. Whereas all the other ones had whole number bases. Okay, maybe we'll deal with that. Looks good. Grace's group, did you think of something? Or what you did is already up there? You already did that one? Okay. Which one did you do?
The 1, 5, 7, 11.
Oh, the x in the power? Okay. What did you guys do up here?
7 and 11. X is a power negative.
Negative power. Okay. Gentlemen? You did this one, negative in the power. Okay. The fractional bases. Okay. And ladies in the back?
We basically figured out that like each equation it was like opposite depending on either the exponent or if it's negative, so we like divide them in half and do like one version of the equation and the other. Does that make sense?
Can you say it again? I thought I followed, but then I... Okay.
So like for example, like 9 and 4 like have the same like not 9 and 4. 9 and 3 have like the same numbers, but like something's like slightly off, like the exponent, like there's a negative x in 9 and it's not 3.
So you group them in terms of similar equations.
Yeah.
Gotcha. Okay, so these are similar. They were in one group. You had another one. They were similar. Okay, I gotcha. I love this so far. I'm going to add one in here. If these are all the fractional ones, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. These are whole number bases. Okay, but ultimately, all of the properties that I wanted us to find, you guys did. Okay, so instead of me talking about each one individually, notice how you discover them on your own. Okay, looks good. Now, going back to the drawing board, take a look at all 12 of them again. This time, only look at the graph, okay, not the equation. So I want you to separate the 12 into 2 groups. Again, they might not be equal, but I want you to group them based off the graphs. Okay, give you a few minutes and then we'll go over what you noticed together like we just did.
I have to find one. Yeah, I think. What do you need them for?
Sorry, I didn't get Stanley for many.
It's just they're all not. I have growth. So we have growth and not. It does not go. No, I have what else one. Yeah, that's actually. Would this be growth? Like actually, nothing will happen. Let's take a look at the blue.
So if it approaches 0,
That's also, I tried to.
We got three groups now.
Get him a package.
Yeah.
This is the package.
What's the deal?
This one's
No, you don't.
No, it's not.
Like we're left for like a minute and a half.
I chew rubber, so like. They taste so good. It tastes so good. And it's we gotta do this.
We did.
It's the case it approaches the
Oh yeah,
Wait.
3 groups.
I mean, that's what I meant. See, it starts here, therefore it doesn't approach it.
3 groups.
It ends
What? How did you categorize it? Side of the graph.
Okay, goes to this. That's a real question.
I picked one that had negative horizontal symmetry and then positive horizontal. I can't talk about these ones.
All right, let's check out these graphs. We're going to work backwards. Ladies in the back, can you give us one of your groups?
8, 12, 10.
And what did they all have in common?
They all below that horizontal axis.
Below horizontal asymptote. Good. Okay. My 3 gentlemen, did you come up with a group?
Yeah, we had 4, 11, 6, 9, and 1.
Okay.
They're all above the horizontal axis.
All right. So, where's 3? Where's 2? Where's 5? Where's 7? If these are the only ones below and these are the only ones above, we're missing some.
Wait, we got some more above.
We got some more above? Okay.
7, 2, 3, and 5.
I like those. Okay. So all those are above. Okay? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There we go. All accounted for. Okay. Noah, did you come up with anything?
Once that's 7 and 12, the horizontal asymptote is above the x-axis.
Ooh, okay, so horizontal asymptote is above the x-axis. So not only can we start to look at if the graph itself is above or below the asymptote, but maybe we can see where the asymptote's located, above the x-axis or below the x-axis, meaning positive or negative. I like it. So that would mean the other one's not listed. The horizontal asymptote is either on the x-axis or below it. Okay, looks good. Did you guys have a group? Or is it already listed?
Yeah, it was the first one.
Below and above?
Yeah.
Okay. Did you guys do something?
Yeah.
Okay.
Did we do this one yet? No, we didn't. Okay, so we got 4, 9, 6, 11, 1, 10, and 12, and those all go away from the asymptote, like they're as x approaches infinity, they don't approach that asymptote.
Okay, so we're going to take a look at 12, which is one of the ones that Travis stated, but maybe also take a look at 5. Notice how if you look at the shape of the graph, okay, on the right-hand side, 12 is moving away from the horizontal asymptote. It's going down forever. Whereas for number 5 on the right-hand side, we're moving towards the asymptote. Okay, so there's a difference between the two, whether you're moving away or towards that horizontal asymptote. So these are moving away from horizontal asymptote to the right. Okay, maybe we'll list the other ones. So that'd be 2, 3, 5, 7, 8. I think that's it. Okay, so these move towards horizontal asymptote to the right. All right. Maggie's group. Did you come up with a different pairing or different? The same. Okay, the other one. Gotcha. Erica, did you think of something different?
No.
No, it's already up there? Okay. Already up there? Already up there. Okay, so because it's a bigger class, obviously we're thinking of some of the same characteristics, which is perfectly fine, okay? But notice how we're starting to think about different characteristics that we can pick apart on a graph, okay? So all of these, horizontal asymptote, above horizontal asymptote, maybe where the horizontal asymptote is located, all of these dealt with the horizontal asymptote. So that's probably a pretty important characteristic about an exponential function. Okay, and we're going to dive into that. Let's see, for instance, if we can possibly make our first connection. Okay, now I want you to look at the graph and the equation together. Try to find a connection with the horizontal asymptote. Look at the graph. Okay, pick any of the 12 that you want. Pick a graph. Look at where the asymptote is located and how that location is related to the equation. I'll put a few up here. Can we make our first connection? Do you see it? Yeah? The constant, the number on the end. Look, okay, so positive 2, horizontal asymptote at 2. Negative 4, horizontal asymptote negative 4. Negative 1, asymptote negative 1. Negative 2, asymptote negative 2. Do you see it? Yeah? Okay, we have our first connection. There's going to be many more as this unit goes on, but we have our first connection. So let's start to think about how we can determine what a specific number in the equation is actually telling us about the graph. So exponential functions typically have this form, okay, A, B, C, D. Depending on where a number is located is going to tell us something different about the graph. What can we say this letter D represents in terms of the graph? That's your horizontal asymptote, okay? What does, now these might not be related to the graph, but maybe it's some vocabulary word that we should be familiar with. What is the B representing in the equation? B stands for base. All right, and what about the A out front? That is your leading coefficient. Okay, the number in front of the base. Now, the base will never ever be negative. So if you happen to have a negative in front of the base, that's your leading coefficient. Okay, the base is never negative. So looking at our first equation, we don't really have a graph to relate this to, but where's the horizontal asymptote going to be located? Do we know that? Where is it? Negative 2. Okay, without even having a picture, we know where a characteristic is. So I just want us to get familiar with identifying these different pieces in the equation, because we're eventually going to know, like, if B is a certain number, what does the graph look like? If A is a certain number, what does the graph look like? Okay, we already know if D is a number, that means a horizontal asymptote. So we're eventually going to get to the point where a certain number is going to tell us something about the graph. What is our leading coefficient in this example? What's our number in front of the base? Maybe we'll start with the base. Can we label what that is? What is being raised to a power? Yeah? 3 halves. Okay? So what's the number in front of the 3 halves? 1. It's an understood 1. All right. Now the value of C, I know C is coming from the power spot, but notice how if you were to plug in C for this x, it would make the power 0. I want you to maybe think about it that way. What number can you plug into this power that would make it 0? 2. Okay, that's our value for C. And our value for D is -2, and we said that's our horizontal asymptote. Now, actually, one of the characteristics that you guys noticed based off the equation is whether the x in the power is negative or the leading coefficient is negative. And if we think way back to the beginning of the year when we dealt with negatives, those displayed or kind of told us something about a reflection if we were folding the graph in some way. So do we remember the difference between an x-axis reflection and a y-axis reflection? Where's the negative located if it's an x-axis reflection? Or a y-axis? Let's think about this. What shape of graph is x squared? Parabola. What if I make it negative x squared? What happens? You have an idea, Noah?
Well, I have a question.
Yeah, go ahead.
Isn't the value of C -2 because the formula is minus C?
Yes, but notice how this x in the formula is not negative, and this one is. So that switches it. You have that extra negative in there. Okay, good question. All right, if we have a regular x squared, we know it's a regular U-shaped parabola. If it's a negative x squared, it flips it upside down. So if we have a negative out front, that's our x-axis flip. So x-axis reflection is a negative leading coefficient. Okay, a negative out front. In terms of these exponential functions, if we have a y-axis flip, we need a negative x in the power. Okay, that was one of the characteristics you noticed from the top. So do we have, in this first example, either a negative leading coefficient or a negative x in the power? We have a negative x in the power. So this graph would display a y-axis flip. Somehow we flipped it left and right. All right, let's try 2. Can we see if there's a leading coefficient out front? Remember, a base will never be negative. So, yeah? -1, okay? Which means the base is 3. The value of C, the number that would make the power 0, would be 1. And our D value, which we now know represents a horizontal asymptote, would be 2. Can we identify any reflections for this example? Either a negative leading coefficient or a negative x in the power. Yeah? Okay. It's an x-axis flip. All right, I want you to try the next 3. Fill in the different values. Okay, this is important because we're eventually going to get to the point where we can just look at an equation and say, oh, this number means this, or that number means this. Okay, so we have to identify what each number means, where it's located in the equation, because that's going to tell us something about the graph.
Jim is somewhat fun. Do you have anybody that you actually enjoy spending time with in here?
All right, seems like we're done. We're going to do these rapid fire. Okay, we're just going to work our way around the room. Caitlin, can you give us a value for 3? 2. Blake, the base. 2/3. Elsie, our C value. 1. Olivia, our horizontal asymptote. Okay, that's our D value. Good. Erica, did you identify a reflection? No. Good. We don't have a negative in the X spot or a negative out front. Okay, so we did not flip this graph at all. How do we do for number 3? Good? Okay. Lizzie, can you do A for number 4? -1. All right. Travis, our base. 2/3. River, our C value. 2. All right. Maggie, our horizontal asymptote. 3. All right. And Grace, any reflections? Okay. We had a negative out front. Okay, that's our leading coefficient. Is there another one? And a y-axis. Okay, negative in the x. You could have both. You flipped it both ways. Okay. How we do for 4? Good. All right, Lincoln, our A value for 5. -3. Robbie, our base. Looks good. Noah, our C value. -1. Carter, our horizontal asymptote. -1. And Jack, a reflection. X-axis. Good. We had a negative leading coefficient. How do we do for 5? Perfect. Okay. We're going to continue with these connections or different things to look for tomorrow.
This stuff is like